Oh, that's not what I want to do. I don't have a Gmail account. I think that's that. I think that's the right person. All right. No, I think he's watching the recordings anyway. But anyway, let's see. Today we're going to talk about two-dimensional collisions with conservation momentum. So far, we did linear momentum. So we learned that momentum is this thing that things that are moving with mass have. It's kind of interesting because, again, we come back to Einstein. Our friend Einstein did a lot of things in the past century. One of the things was that he was able to prove that not only do things with mass carry momentum, but things that have no mass can carry momentum, like light. And that's really quite interesting. That's actually the reason that a tail of a comet is always pointing away from a sun or a star when it gets close to a star, is because the sun, or our sun in particular, that's where we usually see this happening. But as our sun shines light out into the space around it, the light carries momentum. It actually has momentum, even though it has no mass, which is kind of strange, but it's true. And the details are in the mathematics of Einstein's theory of relativity. But this momentum actually can push on things like the particles of gas that are surrounding a comet. A comet is usually a ball of ice and rock. And the ice, as it gets close to the sun, even the rock, as it gets close to the sun, actually starts to turn into gas, starts to melt and then to evaporate into gas. And then as it evaporates into gas, it forms this cloud around the comet, and then the light pushes that cloud out into this long tail. So the light is actually causing that to happen. And that was something that was proposed at the time of Newton, like 400 years ago, even before Newton actually. It was proposed by, can't remember, some old guy in Germany or something. But anyway, no, it must have been, he was Dutch, I think. But anyway, point being is that you don't have to have mass to have momentum, but you do have to have some velocity, and light certainly has a lot of velocity. But when we have a massive object, momentum is equal to mass times the velocity, but there is a direction to it. So if you have a momentum in the western direction, that is the exact opposite of the momentum in the eastern direction with the same mass and velocity, because they're in the exact opposite direction. And that's where it starts to get a little bit strange, because several of you emailed me about questions in the homework that talked about momentum being conserved. One of the examples is the cannon. When a cannon shoots a cannonball, here's a cannon. I have a friend who actually built his own Civil War cannon. Has it on a trailer in his backyard. Fires it out into the desert every once in a while. Anyway, you have the cannon and the cannonball inside the cannon like this. This whole thing is mass of the cannon plus mass of the ball to begin with. That's the mass of the entire object. But the velocity of the cannon plus ball is equal to 0. So the momentum of this cannon and ball system before it gets fired is 0. And of course the cannon is on wheels. We didn't put it on wheels, but we should. But then when you fire the cannon moves backwards. You've seen this if you watched like pirate movies or anything. The cannon moves backwards. Not a lot, and not super fast, but it moves backwards. It has some kind of velocity of the cannon, And that velocity is a negative velocity if we consider this direction to be positive. Then this velocity would be negative because the cannon's going to the left. And of course, the cannonball has a huge velocity to the right, which is positive. So how do you set this kind of a problem up? Well, in conservation momentum, all the momentum of the system before has to equal all the momentum of all the parts after. So the momentum of the system before is mc plus mb, because they're one thing. They're all one thing before. They're kind of just sitting here together. They haven't been split apart yet. Times the velocity of the ball times the cannon, which is 0, so that equals 0. The momentum before is equal to 0. The momentum after is equal to the mass of the cannon times the velocity of the cannon. Remember that velocity of the cannon is negative. Plus the mass of the ball times the velocity of the ball. And this equation right here is the one you have to solve. You're going to have a negative mcvc plus mbvv. And what that's going to mean is that mcvc, when you add this to both sides of the equation, has to equal mbvv. And whatever thing you don't know, you can solve for. Maybe they've told you the velocity of the ball and the mass of the ball in the cannon. You want to calculate the velocity of the cannon. Maybe they've told you the velocity of the ball and the velocity of the cannon and the mass of the cannon. You want to know the mass of the ball. It doesn't matter. If you know 3 of these things, you can calculate the 4th one. And this is the conservation of energy equation. And this is the solution to that equation. It creates your formula for answering the problem. This is kind of the reverse of an inelastic collision, where you have two things that are separate and then they come together and stick together and become one. This one starts as one and then splits apart and becomes two, very much like the problems you did yesterday in the lab, where you had the two cars next to each other and you exploded them apart. When they were next to each other, they had a combined velocity of 0, and so they had a combined momentum of 0. But when they split apart, they had different velocities on different sides, different masses on different sides, so they had different momentums. But one of those momentums was certainly in the opposite direction as the other, and so they would cancel out in some way, and you would be able to solve for them. And that's how you do that kind of problem. Anybody have any questions about this conservation of energy kind of problem here? Sorry, conservation of momentum, not energy. Now the other thing, another kind of problem that we had in this chapter is the problem where you have, let's see, well, I think the baseball and the bat was a good one. You have a pitcher throwing the baseball. Let's see if I can draw a picture throwing a baseball. Woohoo! No. That's backwards. Whatever. And this ball is coming down here pretty fast. With some velocity of the ball. We'll call this velocity of ball 1. And let's say that to the right is going to be positive again. So velocity ball 1 is definitely going to be a negative number. And then the batter over here, I can't draw. Here's my batter. He's going to hit the ball, and after he hits the ball is going straight back at the pitcher with velocity ball 1, or velocity ball 2, we'll call it. And this one is definitely positive because it's going in the right-hand direction. And they want to know how much force does the bat hit the ball with, maybe something like that. If the bat is in contact with the ball And let's say that they say the time of contact is 0.03 seconds or something. Or whatever it is, right? So what is the force of the force? The bat equals what? Right? Well, in this situation, we don't necessarily have a conservation energy equation because the bat came in and hit the ball. When you have an outside force coming in and doing something, that negates this conservation of momentum because the bat added momentum or changed the momentum of the system. Right? If they were asking what was the momentum of the bat after it hit the ball, then that might be something we could deal with in conservation of momentum, but we're not doing that. We're just talking about the ball. We're talking about the change in velocity of the ball and the force that the bat applies. So in this case, we have to use what is called the impulse momentum theorem or something like this, right? The impulse is defined as the change in momentum. Change in momentum, of course, is m times v final minus m times v initial. And it's also equal to the force times the change in time. So the change in time is going to be the 0.3 seconds. And you're going to use these two velocities. The negative velocity, which is ball 1, is going to be your initial velocity right here. So that's going to end up making this a double negative. You're going to have a negative and a negative here, and that's going to make this a positive. And then you put in your positive one here, and that's going to make this one just whatever it is. And then you're going to get these two momentums, do the math, equals force times delta t. You'll divide everything by delta t to get just the force. Okay. And then you would calculate the force. All right? Any questions about the impulse momentum theorem? Impulse, is that what they call it? Impulse momentum. Now they call it in the book. Just call it the impulse momentum equation, whatever. So momentum. Here's the force equals change in momentum over t, so that force times t equals the change in momentum, right? And that gives us the lead-in for the impulse momentum theorem, which is somewhere along through here. There you go, impulse momentum. And then the conservation momentum equation here, where the initial momentum equals the final momentum. Now, there's another situation, and that is the elastic collision. And I don't remember if I gave you homework on this. I probably did, but in an elastic collision, this one is different in that the two bodies that collide with each other always stay separate. They're never together, stuck together, one thing. They're always separate things. If they do interact, they just bounce off each other perfectly and don't have any more interaction other than a bounce. But within that bounce, they can exchange two things. They can exchange kinetic energies, and they can exchange momentums. In other words, one of them might start with more momentum and more kinetic energy, and then after the collision, it might be the other way around. The other one might have more kinetic energy and more momentum. Or it might just be one or the other that changes. Or one goes up and one goes down. That can happen too, actually. I think it can. But because both momentum and kinetic energy are conserved, then you have the momentums added together at the beginning equal the momentums added together at the end. And it's always there's always one momentum on each side of the equation for each object. So in this case, two objects, you can have two momentums on the left, two momentums on the right. And that is absolutely true for perfectly elastic collisions, no outside forces. But you will also have a second equation where you have just as many kinetic energies on each side of the equation as you have objects. And then same on the other side of the equation. So now you have two different equations that you can solve for. You can solve one of them for one variable, plug it into the other equation, and get one equation with only one variable, and then solve it and plug things back in, kind of like we've done before. And we did that with this example where let's see, where is it? Oh, here it is. I guess that's the drawing for it. So we have this situation where two objects bounce off of each other with a perfect bounce. You can imagine them being magnets and they're repelling each other so that they have a perfect bounce with very little loss in energy, very little loss in anything. And so we consider it to be a perfectly elastic collision, where therefore the kinetic energies at the beginning equal the kinetic energies at the end, all added together. And all the momentums at the beginning add up to be all the momentums at the end. Doesn't mean that they will always be the same on both sides of the equations. It just means that the sum of all of the different momentums will be the same on both sides of the equation. But the momentums themselves can go up and down for each individual object. All right. And then the inelastic collision, which we've already talked about, like with the cannon, and in this particular section, we did the goalie catching the puck or whatever. A good example of that. In your lab yesterday, you did the two cars stuck together at the beginning, and then they explode apart from the spring in between them. It's like a reverse. It's like a reverse inelastic collision. But now we got to get a little bit crazy. What happens if we're not just doing this in one dimension? It's not just one thing hitting another thing and they both move in a straight line with each other, right? What happens if you have like pool cues, where you have pool balls. Pool balls, one ball, pool ball hitting another one, but it doesn't hit it perfectly dead on. Hits it off to the side a little bit so that the red ball goes down, the purple ball goes up. What happens in this situation? And it turns out that nature doesn't really even care what the situation is. As far as nature is concerned, momentum is always conserved. We've never observed it to be otherwise, and this is no different. Momentum is still conserved here. But you have to, again, add all the momentums together at the beginning and all the momentums together at the end. But also, in addition to that, we have to keep track of the momentums in the x direction and the momentums in the y direction. So what we have to do, we have to split up our velocities into x and y components. Now tell me, how much momentum does the purple ball have in the y dimension? If this up and down is the y dimension, how much momentum does the purple ball have in the y dimension when it's the only one moving along this direction? Why 0? Because all of its velocity is in the x direction. And momentum depends on the direction of velocity. So if there's no direction of your velocity is pointing in the y direction, you're only moving in the x direction, you have 0 y momentum. So when we set up a problem like this, we want to set it up in two parts. The x momentums and the y momentums and then deal with them from there. You can still use the kinetic energies without directions, because kinetic energies don't care about directions, right? So the equation with the kinetic energies, if this is a perfectly elastic collision, and it's pretty close to that, but if we're considering this a perfectly elastic collision, then you can still use the kinetic energy equation just as it is. But the momentum equation has to be split into the x and y, and then afterwards, does the purple ball, after it hits the red ball, does it have some y-dimensional momentum now? Yeah, because part of it is now pointing upward, and then the red ball also has some y-dimension momentum, right? But can you tell, is it obvious to you that this momentum of the y part of the momentum for the purple ball plus the y part of the momentum for the red ball must be exactly equal but opposite? Does that make sense to you why that would be? How much momentum did the red ball have before it got hit? Is it moving at all? No. It has zero momentum in the x or the y. So the y-dimensional momentum to begin with is 0 for the purple ball, 0 for the red ball. So we start off with 0 y-dimensional momentum. 0 momentum in the y direction. At the end, when these balls are going up and down off to these angles, how much momentum should we have in the y dimension if momentum is conserved? It should be exactly 0. So this one has to equal this one, except in opposite directions, right? They have to be equal and opposite. In other words, if they're not, then they won't add together to be 0. And they have to add together to be 0 because they started with 0. The x dimension is a whole different thing. The x dimension, we start off with some momentum. We end up with 2 balls that have momentum in the x direction. But in the y direction, we start with 0. We have to end with 0. So the first equation we get from this is that the y-dimensional momentum has to equal 0. In the x direction, it's going to be the same as always. You're going to have the momentum in the x direction from the first ball, momentum in the x direction from the second ball, which happens to be 0 because it's not moving at all, is going to equal the final momentum in the x direction from the first ball plus the final momentum for the second ball in the x direction. And the first one's going to be 0, so that one's going to drop out, and we're going to get this equation when we finish it up. And then we can go ahead and solve this. Well, sorry, we're not done yet. Remember, both of these ones have components we have to deal with. So this one is going to be velocity 1 times the cosine of theta 1 to get us this component along the x-axis. And this one here is going to be v2 cosine theta 2. And you're going to add those two momentums together, and then that is going to have to equal the momentum that it had to start with in the x direction, which is what they're doing here. So there's their cosines and their cosines. So in this particular case, the conservation momentum in x looks like this. The conservation momentum in y looks like this. But that is not absolutely true for all conservational momentums. For all conservational momentums, x or y, whatever, in any situation, it always looks like, where is it? It always essentially looks like this. If we take off the y here, the momentum of the first one in the y or the x or the z or whatever direction, plus the other ones that are for other objects in that in the beginning of the problem, whatever, however many you have, and then those have to equal the final momentums for each one of those objects in the same dimension. This is the y dimension. You can write it for the x dimension, write it for the z dimension if you know whatever you want. So this is a tricky example. And the reason they give this example is because this is a real life, excuse me, this is a real life use for this. This is what we call, you could call this spectroscopy, I suppose, spatial or mass and spatial, it doesn't matter. It's a way of looking at things that you can't literally see. Can you think of anything that we want to look at, quote unquote, that we can't actually see? So the waves that our eyes detect, the wavelengths of light that come in and our eyes see things like color, range from about 400 to 700 nanometers in length. Okay? 400 to 700. That's if you get up to 1,000 nanometers, and 1,000 nanometers is a millimeter. No, it's a micrometer. So 1,000 nanometers is a millionth of a meter, which is a thousandth of a millimeter, which is 1,000 times smaller than that right there. Okay? 1,000 times smaller as you could, if as close as you can get your fingers together without touching them, that's about a millimeter. And you split that into 1,000 pieces, that's a micron or a micrometer. And then you go a little bit smaller than that, and that's the wavelength, that's the length of the waves that our eyes see. Okay? Anything that is smaller than that wavelength, anything smaller than 1,000 times smaller than this, we cannot see at all. And atoms are 1,000 times smaller than the light that we see. Okay? So, I mean, the best analogy of it is if you're trying to measure something. You've got this ruler here. So I've got a ruler. And the smallest marking on this ruler is a millimeter. And if I'm really careful, I can measure things down to about 1/2 of a millimeter. You know, I could guess 1/2 a millimeter by looking at this. I couldn't guess much more than that. I might be able to get, I might be able to guess something at, close to 1/10. So if something looked like it was about 1/10 or 2/10 or 3/10 of a millimeter, I might be able to guess that, but I wouldn't be very accurate. But I would guess down to about 1/2 a millimeter. I can be pretty accurate with this ruler and see the measurement, right? But if I was using this thing to measure, if I was trying to do some science and I was using this to measure hairs from my dog's fur, right? Trying to measure the thickness of the hair. How thick is the hair? My measurements would be really far off because I can't really. A dog's hair usually has a very fine hair, and probably way less than 1/10 of a millimeter. I'm just never going to get that. I'm never going to be able to say, well, that one's this. That's not happening because the tools that I'm using are just not the right scale, right? In order to see something like atoms, we really have to use something about as small as atoms. And so what they often do when they can't see something like an atom or something like something small like an atom, like a molecule, they'll actually send something else in instead of light to look at it. Instead of shining a light on it, maybe they'll just shoot some electrons at it. Why not? Or maybe they'll shoot some other things at it. They'll just start firing particles at it and seeing where they bounce. Right? And if they bounce off in funny ways, at funny angles, and with funny bits of energy attached to them and everything else, they can actually figure out a lot. It's pretty amazing what they can figure out. This is the way that DNA was discovered. So